Hello, welcome to our course Solar Electric Power Systems. We talk about solar irradiance today, then we go to solar thermal systems and photovoltaic energy conversion. We learn the basics, applications and actual developments. This semester, this course takes probably place as a complete online course, so we have these videos, but there's also a PDF of the PowerPoint presentation on the PAL system. It's 1.5 hours, this course, then there will be an exercise. And the test of all 15 course parts will take on July 2020. My name is Stefan Krauter. I'm chair of the group Electrical Energy Technology and Sustainable Energy Concepts. You'll find more information on our website. We work on energy efficient buildings. In general, we work on sustainable energy generation of use of energy. So this contains energy efficient buildings, wind power, monitoring decentralized energy systems, about virtual energy storage. I explain it later when we come to the storage part, about load shifting. So we don't have to install a lot of storage. We can shift the load to times when we have more solar energy, for example, available. We work also on energy yield prediction and optimizations of photovoltaics. I studied in Munich in electrical engineering. Then in 1993, I made my PhD at the University of Technology in Berlin, also about photovoltaics, about operation model of photovoltaic modules. We found a company called Solon to manufacture PV modules in Berlin. I made my habilitation in 1998, also dealing with photovoltaics, but also relating the environmental aspect, so how much carbon dioxide is emitted during fabrication and how much carbon dioxide we can avoid using photovoltaics. Then I was for almost 10 years in Brazil at the Federal University of Rio de Janeiro, was giving lectures. We set also up renewable energy labs, and we made events on renewables to avoid climate change. Back in Germany, we found in 2006 the Photovoltaic Institute in Berlin, where we do testing and certification of PV modules and systems. In 2008, I received a call to the University of Applied Science in Biberach on energy systems. And since 2010, I'm here in Paderborn at the also a vice director at the Competence Center for Sustainable Energy Technology, CET. Just a short overview on the lecture. So today we will start about the potential of solar energy, the properties of the irradiance and shadowing. Then next week we will talk about concentration of solar energy, solar thermal systems, and then we came to the main part to photovoltaic energy conversion, about the manufacturing of photovoltaic conversion devices. Then we go to solar modules, check the characteristics and their performance. Then we go more towards systems, so what's around the PV modules, the wiring, the inverters, a grid connection, system configurations. Then we see also second part of the system part is the mounting, so-called BOS, that means a balance of systems part, so ground environment and so on, and costs related to that. And then we talk about also off-grid systems versus on-grid systems, its costs and the actual market development, the off-grid markets, and the effect of feed-in tariffs or self-sustainable markets. And then we see the performance, not only electrical performance, we also see optical performance, thermal performance, the simulation of that, the measurements. And then we go about the lifetime of the PV systems, the durability, what standards are there, what kind of degradation effects we have. And the 10th lecture will be about energy storage. So how we can store the energy during nighttime and during wintertime. Then we see also, as an example, how to set up a large-scale PV power systems, all the bureaucracy related to that. Usually we do then an excursion to a renewable energy project. Let's see, that's not for sure yet. So first, an estimation about the potential of solar energy. How much do you guess is the contribution of solar energy to our living? 1%? Okay, some people of you think 1% to 5%, 20%. No, it's actually 94%. How we come to that number? So without the sun, our planet would be much, much cooler. So we only can have a temperature of 14.5 degrees. That's the average global surface temperature due to the sun. And without that heat source, we would have very cold temperatures and no life on that planet. And if we would do that artificially, just we would buy big heaters, and we would need about 15 times the actual energy consumption we already use today. So that's about 15 times 429.4 exajoule. Exajoule is 10 to a power of 18 joule. So that's a really already enormous number what we consume today, but that would be 15 times that value. If you see the conventional resources, such as coal, oil, and gas, they actually derive from photosynthesis. That means also from the sun. Speaking also about solar energy, it took a long time for them to come into existence. About 100 million years. It was set up 150 million years ago in the age of the carbon. And we use that big resources up pretty quickly within about 200 years, and then it's not anything left. Let's take a look if we put that into a relation. First, let's take a look at the greenhouse effect. Besides the limited resources, there's another effect, the emission of carbon dioxide, which is not poisonous or so, or even transparent. But the effect of carbon dioxide, it's transparent for the visible part of the sunlight, so everything we see from the sun is not affected by carbon dioxide. But if we go to the emission of the surface of the Earth, as we learned, it's 14.5 degrees in average. It doesn't let pass that infrared emission emitted by that surface. And that's a greenhouse effect. So we have an increase in temperature, which is generally not bad. So without the greenhouse effect, our temperature would be about 33 degrees Celsius colder than we have now. So one part is positive, but now we are exaggerating it, and we have an additional increase in temperature. It's not only about carbon dioxide, there are other greenhouse gases such as methane and so on. So all these greenhouse together have an effect that increases the temperature. There are some uncertainties, just as cloud cover or the degradation of the woods and so on. But in general, all major institutes agree that the even temperature decrease between 2 or 5 degrees or even more. And these have severe effects. So we see here, this is a graph with some estimations by MIT, which see that it's 2 degrees of the Paris climate agreements. If we go beyond that, what will happen? So what we already see now, even at lower effects, that the crop yields fall, not so much in Germany, but if you go to Africa or to the United States and so on, we see already problems with the crop yields. Glaciers melt, we also perceive, even here in Europe a lot. We also see already water shortages, at least temporary in Europe, but permanently in other regions of the world. And if we go beyond 40 degrees, we also will have rising seas, which will pose severe problems. What we also see now is reef gut damage. Here, the Great Barrier Reef in Australia got totally bleached. We already see also species extinctions. We see more frequent or more severe storms, droughts and fires and heat waves. And it can even happen, if you go to the very last part, that there will be a feedback loop, and we will have an abrupt climate change. For example, here with the North Atlantic jet streams, they already slow down, and they are causing these omega situations in the weather. What it means, so we have sometimes very long periods of good weather. So many people like that, but it's also related to droughts. So let's take a look to the possible solutions. So first, let's take a look to the existing energy consumption. So this small red cube represents the world's energy consumption during 1 year. And as we saw, we have some resources. We have the conventional resources. We have put them into relation. So we can't use up them very often. They are limited, and they not get replaced, or replaced only in a very, very long time periods. But also even uranium is limited, so we cannot feed the whole world's energy thirst only by nuclear power. There is a limitation to that. Coal lasts a bit longer, but as you know, it's related to carbon dioxide emissions, same to a lesser extent to oil and gas resources. So how much would be our potential for solar energy? So if we take a look at how much solar energy hits the surface of the Earth within 1 year, we come to that cube. That is, the orange cube represents the solar energy available only during 1 year. And so it's much more than all known resources, and much, much more, about 14,000 times more than the world's energy consumption we have today. So enormous resource, so we have to use only a very small amount of that, exactly a 15,000 or 14,000 of that amount, if we would have a conversion device with 100% of conversion efficiency. If we use quite conservative technology, take about 10% of conversion efficiency, we come to that graph. So this is a global solar power plant placed on inhabited areas, just like the Sahara Desert. You see just also quite conservatively calculated with a 10% of conversion efficiency from sunlight into electricity or other resources which can derive from the electricity. And you see that's big, but not really not really out of the scale. For Europe, would be much smaller. Also for Brazil and Germany, which has about the same energy consumption, it's almost not really visible on the satellite image. If we would distribute that huge power plant into smaller parts over the planet, so you see this black dots or the black circles here, so we would need less wires. Additionally, there is an advantage, so we could overcome day and night, because when there is nighttime in Europe and Asia, it's daytime in United States. Even the seasonal changes can be overcome. So when there's winter in the northern hemisphere, it's summer in the southern hemisphere. So we can get during winter time this solar energy from there. If we would have just a kind of, this is global grid. The nominal power of the power plants would be about 18 terawatts nominal power. These are the costs. This is about 10 years ago what has been estimated. So we see wind was estimated 3 to 4 cents per kilowatt hour. It's all prices per kilowatt hour. It's mentioned here. Yes, it's mentioned on the y-axis. For solar, it was expected 20 cents per kilowatt hour. I come to this a bit later. Geothermal 3 cents, solar thermal 6 to 7 cents, and biomass 6 to 7 cents. So besides solar, all the prediction came true. By solar, it was much more positive than the actual predictions. We now have only a tenth of that. In sunny locations, we actually can generate electricity for 2 cents per kilowatt hour. So it's not only cheapest source of renewable energies, it's the cheapest source of energy of all. Even in Germany, we can go 6 cents is written here. I know some projects where already 5 cents per kilowatt hour have been reached. So, very positive issues about solar energy. So we talk about how is it generated and how we can make use of that. So first, let's go to the source, the sun. The sun actually is a fusion reactor with lots of power. This is 4 times 10 to a power of 20 megawatts. The actual fusion takes place in the center of the sun, which is really, really hot, about 15 million degrees Kelvin. What we see from the sun is actually only the relatively cool surface, so-called photosphere, which emits also the solar radiance with a temperature of about 6,000 Kelvin or 5,800 Kelvin. According to Planck's law, we have this formula here. We have a certain temperature, and then you have this curve, and if you have this temperature, the maximum of emission takes place at about in the vicinity of 550 nanometers of wavelength. That's also the maximum sensitivity of the human eye. This is about the color yellow and greenish. If we go to lower wavelengths, then we have the blue part, and if you go even lower, we have the ultraviolet part. If you go to in the other direction, we can see up to 800 nanometers, that's the color red. Beyond that, that is called infrared radiation. The Earth is quite far away from that, so we can, so about 150 million kilometers. So one ray from the sun takes about 8 minutes to reach our planet. That's not in scale. So we will see later how much is the real scale is. And we get about 178 petawatts in power is received on above the Earth's atmosphere, so not on the ground level, but on the satellite's sphere. And as I told, it's more than enough for 14,000 times the world's energy consumption. As I told, we will take a look at the real scale of the sun and the distance. So that is actually real scale. So that's the diameter of the sun on the left side, and you see here the Earth is really, really small in comparison to that. So the sun has a diameter that is 109 times bigger than the diameter of Earth. So really big. That's also not the actual distance. So here I put a graph with the actual distance. So here you see the same above. You see very well the sun still, but Earth is almost invisible in the actual distance of related to the 150 million kilometers. The capturing angle is about 1 degree. So even if you have only see the sun from 1 degree opening angle, here we have still this enormous power of 178 petawatt. So the Earth is circulating the sun in that distance, 150 million kilometers. So that's also not of scale. But this graph wants to show that the rotation axis of the sun, the rotation axis of the Earth around the sun and the outer rotation are not parallel. It was a big accident, a big crash a very long time ago. People think also about during that crash, the moon came into existence, and the axis has been tilted of the outer rotation of the Earth. It has been tilted to an angle of 23.5 degrees. What impact has that? So we have in summer the northern hemisphere on the left side is tilted more towards the sun, so the northern hemisphere receives more solar irradiance. We call that summer. If we go further in the front, we have the 22nd, sometimes it's also the 21st of September, and that means during that period the tilt is parallel to the sun, let's just call it like that today. So we don't have any effect of the tilt angle, and the sun is sitting perpendicular on the equator. And then if we come to December, 21st of December, then the northern hemisphere is tilted away from the sun and the southern hemisphere is tilted towards the sun. So it receives more irradiance. That means we have winter in the northern hemisphere and summer in the southern hemisphere. Then we have another time where sun hits the equator. They are called equinox, so the 21st of March as well as the 22nd of September. On above the atmosphere, we receive the so-called extraterrestrial irradiance, or AM0. We come to this a bit later. This has been very well measured by satellites and so on. This is a value of 1,367 watt per square meter. This changes a bit due to measurement inaccuracies, and also while it's not a perfect circle, it's a little bit elliptic, how the sun, and there are also other effects, so that it's not really very exact, but anyway we call it solar constant, E0. So this is maximum irradiance that we receive on the planet. So if anyone says, okay, we have 1,400 watt per square meter, it couldn't be true, because above the atmosphere we only have 1,367 watt per square meter. So that's the perspective from ground level. So we see the sun at a certain height or elevation angle. According to the Dean, it's called, some people also give zenith angle, but we use the Dean standard. This is gamma S. This is the elevation angle of the sun, indicated by the index S. And then we have also the so-called azimuth angle. If you find some literature, they also take the azimuth angle as a deviation from the southerly direction. We take it according to this Dean standard from the north direction. So it's called alpha, and the index is also S, like the sun. Then we have the atmosphere. We not only have the angle, but the length through the atmosphere depends very much on that angle, and this has some effects. There's some absorption, some scattering, and so on. Therefore, we have to know the path length through the atmosphere, and this is called air mass, AM. So the most simplest way, or the shortest way through the atmosphere would be if the sun would shine perpendicularly on the ground. This is called AM1. So the shortest way through the atmosphere. And for example, what is often used in standards is AM 1.5. That means the path length through the atmosphere is 1.5 times longer than the shortest way, the perpendicular way. And this sure depends on the elevation of the sun, as we learned, gamma S. And if you want to calculate for any other elevation angle, you have AMX is 1 divided by the sinoid of the elevation angle. So if you have 0, for example, it's 1 divided by 0, it's infinite. So we would have an infinite AM. So that's when the sun is on the horizon. The other way, what we see here already is if we have an elevation angle of exactly 90 degrees, it's 1 divided by a sinoid of 90 degrees, which is 1. So we have 1 divided by 1, that's exactly AM1. This is one effect that affects the spectrum of the solar irradiance, the air mass. We see it a bit later, the actual effects of that. First, I want to speak a little bit about the temperature. So we knew from the first slide on the radiance chapter that the surface of the sun has a temperature of about 6,000 kelvins. 5,800 kelvins, and this makes a spectrum where you have the maximum about 500 nanometers or 0.5 micrometers. If you go to lower temperature, for example, in our incandescent light bulbs, we are limited to the maximum supportable temperature by the filament or by the wolfram, and we can only achieve 3,000 Kelvin, and there the emission takes place mostly in the wavelengths of about 1 micrometer. That's already in the infrared region. So ordinary light bulb is more a heat generator rather than a light generator. Uh, these um, these curves are a little bit exaggerated. So we have for the 5400 Kelvin curve, it's amplified by a factor of 3 in the y-axis. For the 3000 Kelvin, it's already amplified 10. Actually, this curve would be much smaller but it's I just wanted to show the quality of the curve and the effect of temperature. This is called Wien's law. An Austrian physicist has discovered this, so you can even have the surface temperature of planets or of suns which are really far away, of stars which are really far away. If you know the spectrum of them, then you can really calculate the temperature according to that. For example, if we have 500 nanometers, we know it's exactly the same surface temperature as our sun. It's about 6000 Kelvin. If it's 1 micrometer, the surface temperature is around 3000 Kelvin and so on. So we are now on the top surface, not on the atmosphere, atmosphere. This is called AM0 radiation in the middle. If we are on the ground level, we have AM 1.5 radiation. If we see the sun elevation, I think it's 41.5 degrees elevation angles. This is how we see it in Paderborn. We never have a perpendicular irradiance of the sun because Paderborn is too much north. We come to this a bit later. So here we see an example for the equator at the different daytimes and the actual elevation angle of the sun. So the black line, what we see here on the top, is at an elevation angle of 90 degrees. That means we have AM1. That occurs during the so-called equinox. That means the 21st of March and the 22nd of September at midday. So we have exactly that situation, and we have a quite strong spectrum with a maximum in the vicinity of 500 nanometers. If you go more towards the afternoon, for example, at 4 o'clock p.m., we will have an elevation angle of gamma S of 30 degrees and an equivalent air mass of 2.0. And so we see already some changes. So first, the intensity is much smaller, but also not only the quantity, also the quality changes. So we see in the 450 nanometer part, there's almost very little left. That means the blue part is completely absorbed in through the part of the atmosphere or scattered. But the red part is also affected, but not to such a large extent. So relatively, we have more red part than blue part, and that's also indicated by the color of the curve. So the sun appears to be more reddish, and if we go down to 10 degrees at about 5:20 p.m. Everybody knows that the sunset, so the sun is totally red, and we don't have any more blue part. We basically have a red and infrared part of the sun irradiance at a very low irradiance level. Why we talk about it? That's important for some solar energy conversion devices, not so much for solar thermal devices, but for photovoltaics, because they only can convert only a part of the spectrum. And therefore, we have to know about these properties of the solar irradiance. If you take a look here, for example, it's a nice graph from Berlin about the different elevations and angles of the sun during the different parts of the season. So same as for Paderborn, we never reach AM1. The highest angle we can reach in Berlin at the 21st of June is 60.8 degrees, while Paderborn is a little bit more south, exactly 0.6 degrees more south. We can have a higher angle. That means we have 61.4 wait a minute, yes, 61.4 degrees in Paderborn as the highest elevation angles at midday at the 21st of June. And that is equivalent, according to the formula you saw before, to AM 1.15. We are not in June yet, we are more in April. So here for the 1st of April, we exactly have that number, which is very often used for the standard, AM 1.5, at an elevation angle of 41.8 degrees. If we are more in earlier in spring or later in autumn, we have an elevation angle that is midday, for example, at the 2nd of March or 12th of October of 30 degrees. That's equivalent to AM2. And in winter and late autumn, it only can reach to AM3. And if you go to a lowest position at 21st or 22nd of September, that's a bit changing every year, we have about AM4, and that's equivalent to an elevation angle of 14.1 degrees in Berlin or 14.7 degrees in Paderborn. On the top we have, yes, the irradiance by the sun directly is about AM0, as you saw before on the spectra. Here we see not only the seasonal change, but also the course of the sun during daytime. So we have a solar azimuth of 180 degrees in the middle. That's equivalent to the southerly direction you see on the upper part. So S means south, SE means southeast. If you go more towards left, it's east and northeast. Then we have southern direction mostly at midday, not exactly. That's depending on the position of the location where you do these measurements. And if you go, for example, to the 21st of April, we are very close to that. You see here that we will reach midday an elevation angle of about 50 degrees. So gamma S is 50 degrees, and you can calculate the actual air mass due to that. That's for midday. Sun goes up at that time at 5 o'clock. While we have now daylight saving, it's not exactly 5 o'clock anymore, it's 6 o'clock. And sun goes down then at normal time at about 19, that means 7 o'clock p.m. If we go more towards summer, for example, at the upper line, 21st of June, we see that sun already goes up at 4 o'clock. It's not only east, it's even northeast. It goes up, reaches the southern position at 12 o'clock and goes down at 8 o'clock in the evening. Why we do this? That's important if we have obstacles. So if you install your photovoltaic power plant and you don't have free space, there's a tree there or a house there, it may affect, at least for some parts of the year or some parts of some days, the solar irradiance. Let's take a look at that. And first we take some other locations here. As it's sure, it depends on the location. We saw there's a deviation between Berlin and Paderborn, but if you go more south towards south, for example, here in Cairo, there we see big differences. So we see that the highest angle achievable in Cairo is 83.4 degrees. That's not perpendicular yet, almost perpendicular. So with not AM1, but AM 1.01 at the 21st of June. And the lowest position on midday during the year, also the 22nd of December, is 36.6 degrees, equivalent to AM 1.7. And you see the equivalent curve, what we saw for Berlin. So we have here about the same, but as you see here already, the length of the day are more equal. So we don't have these extremes that sun goes up at 4 o'clock and goes down at 8 o'clock. We just see the best is here in summer. There's a deviation of 1 or 2 hours if you compare it to the winter duration. This is for Brazil. It's on the southern hemisphere, exactly on 23.5 degrees. Southern hemisphere, so remember this number 23.5 degrees. Yes, that's the maximum deviation of the sun from the equator. Means in summertime in Brazil, that's wintertime in Germany, that means exactly the 21st of December. You see it on the right part here in green color, December 21st. Then the sun is in zenith, exactly in zenith at midday. That part, this is different a bit. This is beyond using polar coordinates here. So the center, it's a zenith, and the outer circle is the horizon. And we see here the different positions of the sun during the year and during different parts of the day. Can also calculate it. This is according to the Dean norm. This formula works well for the northern hemisphere. If you go towards the equator, there are some difficulties. Give you in literature some links if you want to really use it for programming and so on. There are some, besides the norm, there are some newer formulas which can even calculate that more accurately. So first part here you see the alpha as the azimuth angle, and this depends on the latitude, on the declination angle. So that's the sun's positions at midday, and also this is the kind of the formula are all there, so we can use it if there's some applications. If you do it here close by, this formula gets unstable if we go if the sun passes the equator. I can even make some corrections here for the sun elevation angle due to the refraction of the atmosphere. This is from the Astronomical Almanac, so some correction factors. Usually due to that effect, the sun shines a little bit longer than it should be. So when it, from the position point of view, it should be already below the horizon. It's still visible, and these are the formulas to calculate it. But this is the effect is really, really very small. We don't really need that for solar energy applications. So what kind of solar irradiance we have? We just basically talked about the so-called direct irradiance. So that's irradiance we see directly from the sun. But if the sun goes through the atmosphere, there's not only absorption, there's also scattering of the sun, and that's the blue part that you see from the sky. So you see one dot, or with the opening angle of 1 degrees, one circle of the sun, and the rest is blue, and that's the so-called diffuse irradiance, mainly scattered irradiance, and this depends on the climatic situation and the weather situation. It can even go up to 100%, but in general we have about 30 to 50% of diffuse irradiance. Then there's another effect that is called albedo, and that's the reflected part. So if sun hits on the ground level, for example in a desert, which is often very reflecting, and then what you see on your receiver, for example your solar collector or your photovoltaic panel, can be also be converted, and this is albedo effect. If the module is very flat on the surface, it won't see any albedo, but if it's at a very steep angle, the albedo plays a significant role, especially if you have high reflecting surfaces like sand or even snow and so on, or water surface. This can have some effects, but a lot of parameters, it depends a lot of position of the sun, the elevation angle, even the height of the module plays a role and so on. If you want to take a quick estimation about the irradiance level and look out, so if there are dark clouds, the irradiance is in the vicinity of 50 to 200 watt per square meter. If you have light clouds, it's 200 to 700 watt per square meter. If it's really light without any clouds, it's in the vicinity of 700 to 1000 watt per square meter. So that's a very quick approximation. If you want to do it more exactly, I talk about the different measure instruments in a minute. First, here we see some examples here for Cairo, the relation between direct irradiance, so that's the light red part here, and the diffuse irradiance. So you see here the best situation is also because it's in the northern hemisphere in June, July. So we have a daily irradiance of about 8.5 to even sometimes almost 9 kilowatt hours per square meter per day. The worst situation here in December and January, but we still have best is 4 kilowatt hours per square meter per day. If you take the worst day, maybe 1 or 2 kilowatt hours per square meter per day. You see that diffuse irradiance part stays more or less the same over the year, and the direct part is most in summer, sure, and more or less in winter time. This is for Berlin. You see for summer, the highest peaks are not so much far away from the Egypt part, so we even can reach almost 8 kilowatt hours per square meter per day. The problem is the winter. There we have well beyond below 1 kilowatt hour per square meter per day, even below 0.5 kilowatt hour per square meter per day. So if we want to do a year around a power supply by photovoltaics, we either have to have very large solar power plants, or we have to store the energy from summer, which is then about 6 times higher than in winter, or even more depending on the day. You see, in wintertime we almost exclusively have diffuse irradiance. For Paderborn, it's a bit better, so irradiance in winter is there a bit more. This shows the extremes here. So the yellow part is our measurements in Berlin in the 2nd of July. So you see here not reaching 1000 watt per square meter of irradiance level, but above 800 watt per square meter. And in winter, for a clear day in winter, we are not so bad. It's for clear day in winter we have 250 watt per square meter. But if you have a very bad day in winter, for example, when the measurement took place at 22nd of December, it's very small. So it's perhaps 20-30 watt per square meter as a maximum. We can equalize that a little bit by tracking. So we direct a surface our receiver or our solar collector towards the sun. So first, the red lines are the fixed part. So this is a part of the sun. What you see here, this is the usual what you receive at the weather stations. So at midday for the 21st of June, you have almost well above 900 watt per square meter. If you would track that during daytime, it would increase a little bit, so a bit above 1000 watt per square meter of irradiance. And in the morning time and in the evening time for this 21st of June, it would even boost also the morning and the evening part. But the most interesting part is for winter. If you take the 20th of December, so if you have a horizontal surface and the incidence angle of the sun, because the sun is only 14 degrees above the horizon, the incidence angle is very flat and we have a lot of reflection, but also a very little projection area on the surface. So the irradiance achievable even at a very clear day is a little bit above 200 watt per square meters. If we would track that, so we would direct the receiver surface towards the sun, then we would have a significant increase to about 700 watt per square meter for a clear day. So it's about almost 2 to 3 times the irradiance we can receive. In general, if you consider also the bad days, that means we have only diffuse irradiance, then the tracking doesn't help a lot. So all over a year, it's between 20 and 30% more irradiance we can receive due to the tracking efforts. This is a comparison of different regions of the world. Above is the Sahara Desert. This is daily irradiance also in kilowatt hour per square meter. So in wintertime, it's even here above 4 kilowatt hours per square meter, and in summer, it's an average 8 kilowatt hours per square meter. On the lower part, we have here London, United Kingdom. So we have a little bit above half, so comparable to Berlin, about kilowatt hours per square meter per day. And in summertime, it's not as good as in Berlin in summer. So we have only 4.5 kilowatt hour per square meter per day. Then we have some tropical locations like South Vietnam. It should be more close to the Sahara curve, but while we have a lot of rain showers and so on, and monsoon times in summer times, the irradiance, the maximum achievable irradiance, very much reduced to this cloudy skies. This is also comparison to Hamburg and some locations in Brazil. While we have been living there for some time, I have a lot of data from there. So it depends very much where you are in Brazil. So if you are in Rio de Janeiro, the irradiance stays almost constant all over the year. This is the red line. Even more to wait a minute, that is going past Porto Alegre. This is more pronounced. Fortaleza is also quite constant, and Porto Alegre, it's 30 degrees south of the equator, and there we have an opposite effect to Hamburg because in the southern hemisphere. So in June, July, irradiance is significantly decreased, and the maximum takes place in January and December. If you have the accumulated values of the irradiance and want to check which is the best positions to position your solar your receiver, you come to this graph. So this is yearly irradiance. So all the irradiance accumulated during 1 year. So that's a unit as kilowatt hours per square meter per year. So you see here the best positions is south with a little bit, not really totally symmetrical, a little bit directed towards east. That's basically because at least in Berlin, the morning seems to be a bit more clearer than the evening. So the irradiance in the morning is a little bit better than the evening. If you incline your receiver, elevation angle of your receiver or your collector or your photovoltaic panel to about 30 degrees, you get the maximum, which is about 1,100 kilowatt hours per square meter per year. If you incline it more, it goes down, but not significantly. Even if you incline it to about 50 degrees, you only have a loss of about 10%. If you install your photovoltaic panel on a facade, on a south directed facade, you will still have above between 800 and 750 watt per square meter. So you have about 30% loss, 35% loss in irradiance level. This was quite significantly in former times, but while photovoltaic got really cheap, so it's cheaper than usual facade elements, that's not as important as it's been some years before. Even if you deviate from the southerly positions, for example, if you go towards east, so if you go install it at a level of 90 degrees east or totally east, you still have a quite high irradiance. So it is not exactly important. Also, therefore, I mentioned the formulas very briefly. So if you deviate 1 or 2 degrees, it doesn't have any big impact at all for the yearly energy yield of your photovoltaic panel. It's a bit different if you consider concentration technologies, so with mirrors and so on, especially parabolic mirrors, you have to do the calculations more accurately. So that is this annual irradiance values in Europe. So you see here the dark green part, that is Paderborn, which means you have about 941 to 980 kilowatt hours per square meter per year. So that's not very good. Berlin is a bit better. So it's about, as you saw on the graph before, about 1061 to 1100 kilowatt hours per square meter per year. If you go more south, for example, Seville in southern Spain, it goes up to almost 2000 kilowatt hour per square meter per year. So here's Paderborn. And you have this value here, 941 to 980 kilowatt hours per square meter per year. If you go to sunny locations, for example, here Seville, southern Spain, then you have about the double, a bit more than the double of irradiance. Here are some calculations, some simulations of the irradiance, not daily, not yearly, but monthly irradiance, so how much irradiance comes there in within 1 month. So if we install it horizontally, like all the measuring instruments in weather stations, so they have irradiance in accumulated during 1 month in average of 78 kilowatt hours per square meter per month. If you incline that a little bit, typically in Central Europe we have about an inclination angle of 30 degrees. Gamma M, so we learned about gamma S is the elevation angle for the sun, and gamma M we use it for the module, for photovoltaic module, for 30 degrees. And there it's looking more a bit towards the sun, because even in Spain the inclination in winter of the sun is very flat, and if you lift up the module a little bit, we receive significantly more irradiance. So from 78 we go up to 112.6 kilowatt hour per square meter per month. If we go towards summer, for example, if we take the month of June, then we have on a horizontal surface 260 kilowatt hours per square meter per month. So horizontal orientation is really good. If we incline the module, we even lose a little bit, not very much, about 5%, but 10%, yes, between 5 and 10%, due to while the sun is already the southern Spain, it's not perpendicular, but it's very close to the zenith, and then the horizontal orientation would be better. If you have a 30 degrees elevation angle, then we lose a little bit. But in general, if you compare the sum, the yearly sum, so for a horizontal irradiance in Seville, we would have 1757 kilowatt hour per square meter per year then. And if we go to the inclination of 30 degrees, then we have 1944 kilowatt hour per square meter per year, plus the advantage that we have a more equalized irradiance. So we have significantly more irradiance in summer when we in winter when we need it, and a little bit less in summer when we don't need so much. So this is also helps a little bit to equalize the availability of sunlight. So another region, this is South Africa. So here the irradiance level are even higher than in Seville. So here you see the brown part, or the beige part is here in the vicinity of 2,400 kilowatt hour per square meter per year. So that means even 20% more than we will have in southern Spain. Yes, also there is even a quick estimations of the available solar electricity, but we come to this more extensively. But just to mention here, if we install 1 kilowatt of a photovoltaic plant, this is indicated here by kilowatt peak. This peak stands for nominal power of a photovoltaic plant. And the kilowatt hours is not for irradiance, but for electrical output. And we would have, for example, if we take the example for a global irradiance of 2,400 kilowatt hours per square meter on the upper scale, and if we go in the lower part here, then we would have 1,800 kilowatt hours of electricity for for a power plant with a nominal power of 1 kilowatt. You can also maps around the whole planet. There are also simulation platforms. For example, this is from Meteornom. The other one was from IRC. There's one NASA and so on. Maybe I give you some links where you can find all this irradiance data. Always the best irradiance data is if you measure it personally, because sometimes satellite measurements are not really accurate. But as I told you, this is less critical in these times than it has been before, because the photovoltaic get quite cheap, and so other factors play a more important role. How much is the cost of land, how much is the balance of systems cost, and how much is the feed-in tariff, and so on. So here you see the most irradiated areas. If you start from the left, here Baja California, Mexico. If you go south here, it's here the Andes, Chile and Bolivia. In the middle, you see here that South Africa and Saharan Africa is the most irradiance, and here if you go to the right part, that Australia is all yellow, and it means that it receives a quite high irradiance levels. How we measure irradiance? So as I mentioned before, you can estimate, but that is very raw. It's just the accuracy is very low. So we measure it, and traditionally we measure it with a so-called pyranometer. It works very simple. So you have two glass domes, and under this glass dome there is a black plate. The sun comes in, gets absorbed at this black plate and heats up. And what we do, we measure the temperature difference of that black plate towards a reference device, or called compensation device. You can measure it directly via a thermal sensor, or what is usually done, use a thermopile or a Seebeck element, and then you have a voltage which is proportional to the temperature difference. And if the pyrometer is well constructed, it's also proportional to the amount of global irradiance, e.g. you see in the middle here. And okay, I can put the mouse here so you see that. This is quite accurate. Also, the advantage of that device, it takes the whole spectrum. So it doesn't matter whether infrared or ultraviolet irradiance, as long as it gets absorbed on this thermal absorber, you get the you measure the irradiance of that. The disadvantage of that kind of measurement device is the lag a little bit, so you have to wait until the thermal absorber is getting hot. Nowadays it takes perhaps 10-15 seconds to do that, but still, if you measure cloud movements and so on, it's a bit too slow. Also, the device is not really cheap. Good pyranometer costs between 1,000 and 2,000 euros. What is often used nowadays is just a silicon sensor, or in other words, a solar cell that you use as a detector here, what you see on the right side. It converts the solar irradiance into a flow of electrons or current. And if you use a shunt resistor, the voltage along that shunt resistor, what you see on the right side here, is proportional to the irradiance. It reacts very quickly, within some micro or milliseconds, but the disadvantage is it only sees some part of the spectrum. Depending on the semiconductor technology you have from the silicon sensor, you see the spectrum of the silicon, or if you have gallium arsenide, it's more in the bluish part and so on. So this depends a little bit on the silicon sensor, and that's gives some inaccuracy if you have different parts of the day. As you know, if in the morning in the evening the spectrum is more reddish, and in the evening part is also reddish, but in midday it's more bluish, and there are some inaccuracy by the silicon sensors. So this is a device where you have 3 pyranometers. On the very left part, as you know already, that's a conventional pyranometer. It measures so-called global irradiance. So irradiance can come from all parts, and it's converted into a voltage which is proportional to the irradiance. These are some milli or microvolts, and you have to amplify that in order to make it measurable in a conventional measurement conversion device. And on the very right part, you see this black ball here on top. This is a so-called measurement device for diffuse irradiance. This is a so-called shadow ball. So it's exactly positioned in such a position so it shadows the sun. So that pyranometer below that, it sees exactly everything beside the sun. So it sees all the diffuse path, but not the sun. And this tube you see in the middle part, this is just designed to measure direct irradiance only if it's directly directed towards the sun. So you have to track it very accurate in the direction of the sun to make good measurements. Here you see in detail, on the left part, the part for diffuse irradiance. On the right part, these tubes were for direct irradiance. You have to, because the opening angle is only 1 degree, so you have to track it at least with a accuracy much higher than 1 degrees. So such a device is a little bit expensive. So if you go back here, such a device costs about in the vicinity of 20,000 euros to have this differentiation. Nowadays, there are different concepts with some integrated shadow ball and a lot of silicon sensors which compute the diffuse and the direct part, but we come to that a little bit later. I know it's already here. That's as a combined device now for the measurements and of direct and diffuse device via complex shadow masks, and you have multiple silicon sensors, and you can compute by the contrast, you can compute the direct and the diffuse part. So this is our roof, not many modules. This is quite an earlier photo. Nowadays everything is covered, what you see here in the middle part with photovoltaic modules. The left part, we have weather measuring stations, which shows here some temperature measurements, wind speed measurements, humidity measurements. Then we have our own custom-made sensor for the diffuse part, and not only measure the diffuse part as a whole, but also differentiates between the different directions of the diffuse part. On the right part, as you already know, there's a pyranometer designed for global irradiance measurement. If you have now inclined surface, you have to also not only consider the position of the sun, so the inclination, as you already know, gamma s and alpha s for the azimuth. We have also take into account the positioning of your receiver, of your photovoltaic module. And there you have, as I already mentioned, gamma E for the receiver and alpha E for the receiver. Sometimes we use gamma M as module or gamma E. So this is derived from the German word Empfänger for receiver and the emitter. And so you can calculate here the actual inclination angle, not only on the flat surface, on the horizontal, but also on the PV module. There are many automated programs which do that nowadays. Also, it's important to know the geometrical position of obstacles. For example, here for a tree which is in front of the house, as you have to know, the elevation angle and the height and so on, to know that, and we take a little bit closer into that. So in order to find out how it affects your energy yield during the year and during different parts of the day, we just make a plot of your obstacles. So we have here the obstacles, and we measure the height as you saw before. Here, for example, here this tree has a height of gamma here. What is it, about 30 degrees or something like this? And we put it in a plot, as you see here. Here's about the highest trees are 20 degrees only in a positions of south, southeast. And do the same for all the other obstacles, not only trees, but houses and everything. And we use our old plot, as you already know, and put those plots together. And there you see the effects of that obstacles. You see first the good news is there's no effect in March, there's no effect in April, there's no effect in June. So sun is much higher than that. But in winter, when we desperately need solar irradiance, especially for if you go to 21st of December, our curve is about 80% covered during the day by these obstacles, and we receive only a very little irradiance, and this translates into very little energy yield. In 21st of February, that's a little bit better, so we have about 80–90% without of the day without obstacles. But if we do really accurate calculations, estimations of the energy yield, we should consider that. And as I mentioned already, after April, we don't have any problems with that. It's not only obstacles, it could be even by your own stuff. So you have here the shadowing by different rows of installed photovoltaic panels. So we calculate it a bit more accurately in the exercise. But first, to give you a rule over the thumb, in Germany, you have an elevation angle of about 30 degrees and adequate height. You should keep it in a distance of 4 to 6 times the height to avoid significant shadowing. If we do it more accurately, we just apply the trigonometric formulas. So we have first the distance of the different rows in D. We have the length of the receiving plate or of our modules. Then we have the height. This depends sure on the elevation angle of your module, of your receiver. And then we have alpha here, as we see here, that's the minimal elevation of the sun. For example, in Berlin, if you have the 21st of December, then this elevation angle is 14.1 degrees at midday, and even lower if you consider earlier parts of the day. And if you have an adequate distance, then at this time of day there is no shadowing. If the sun is lower than that, there will be shadowing. As is mentioned, the alpha 2, which already says that, okay, 50% of the second row, of the area of the second row, is already shadowed. So this is according formulas to that. So we have the height is L times the sinoid of the elevation angle. We split up the D, is it here in D1 and D2. So we have in two triangles. So the D1 triangle we can easily calculate by D1 is L times cosine of the gamma E, so the elevation angle of the sun. And the second part, the D2, the other triangle with the alpha here, and it's H, the height, divided by the tangents of alpha. And if you put it together, you have L times cosine, the first line here, cosine gamma RE. Can you put the mouse here? Yes, the mouse here, so we are here. Cosine gamma E, and then a sinoid gamma e divided by the tangents of alpha. Or we can do it the other way around via the Pythagoras sentence. So we have here the square d square is equal to L square mean minus H square. Or if you take a d, then it's the second root of L square minus H square. For d, sorry, not for d, for d1. This is for d1. And the same for d2 as above, H divided by tangents alpha. And so we come to that formula. So this cosinus gamma e is equivalent to a square root of 1 minus sinoid gamma e in square. You find this formula also, some formulas. So let's see some results. So this is a computed results. So we have here the use of area efficiency. So we would use, if you put all solar panels horizontal, we would have a use of area efficiency of 100%. And then we have the shadowing angle, as I've been mentioning before. For example, in winter times in Berlin, it's about 14 degrees here. If we go to 15 and you come, can we see the mouse here? I guess here, for example, here 14 degrees, come to that. And then if you have a module elevation angle, what's typically usually 30 degrees here, 30 degrees, we come to that curve. And then here for Berlin in winter, if you don't have any shadowing, we have a use of area efficiency of about 35% if you go down here to the x-axis. These are the losses. What you have here in irradiance, 0%, it means you won't have any losses. And here you have here up to 20%. Calculated for all over the year, not only the different seasons, but all the different parts of the day. If we go back to our example, shadowing angle of 14 degrees, we have here 30 degrees of elevation angle. So we have about 5% of shadowing losses through that, if you do that. Okay, and that's the exercise. I just explain and go to details a bit later. So first you have to do the nominal power of your PV module, usually given at the irradiance level of 1000 watt per square meter at perpendicular irradiance, and spectrum equivalent to AM 1.5, and an operation temperature of the modules of 25 degrees, which is not realistic. Usually it's higher, but it's a standard. They are called standard test conditions, or short form is STC. Or as you saw already at the examples of South Africa, it's indicated by an index P at the power. I think it means it's according to standard test conditions. So this, for example, 1 megawatt peak P means, but it has the power plant has a power of 1 megawatt if standard test conditions are applied. And you have to calculate the distance between two rows of modules in order to avoid shadowing, at least during midday. For all over the year, you take the worst case, sure, when the sun is lowest. Yeah, the location here is 23.5 degrees south. That's Rio de Janeiro, Brazil. And also you take it the same amount, the same value as elevation angle for the modules, also 23.5 degrees. So gamma M or gamma E is 23.5 degrees. First questions, does the module has to be directed towards south, north or south? As a hint also. And the modules, they have 300 watt peak. That means just under standard test conditions, nominal power. They have a length of 2 meters and a width of 1 meter, so 2 square meters in total. Then you have to compare which requires less space, horizontal or vertical mounting. How much area would you require if you would install a power plant of a nominal power of 1 megawatt? And what would be the relative saving in the required area if the module elevation angle would be 10 degrees only? So that's your exercise you should do, and come back with the solutions of the exercise, or you already have it uploaded on the poll system. Thanks a lot. So welcome to the first exercise of our course, Solar Electric Power Systems. The first exercise will be about shadowing. So the question is how far we have to keep the distance between rows of solar collectors or solar modules in order to avoid shadowing, especially when the sun is in a very low position. We learned that the lowest position of the sun in winter, 21st of December, for example, is about 14 degrees, so quite low, and the exercise is exactly about that. So we saw the formulas according to that. So we just, in order to calculate it, we divided that triangle up into two triangles with each with a 90 degree corner, and then we were able to calculate the several distances. So the d1 plus d2. The formulas were already in the lecture, so heard, and yes, you can also go via Pythagoras to calculate d1 and so on, and we apply them now in this exercise. So also part of the exercise, in order to keep the was just we apply real solar converters, in this case photovoltaic modules, so converting solar energy into electricity. They are calibrated in so-called standard test conditions. That means the irradiance is fixed at 1000 watt per square meter, which is really high in Germany, which most never happens, and a fixed spectrum at air mass 1.5, and a fixed temperature at 25 degrees, which is really also quite optimistic, because usually the temperature is quite high, and at photovoltaic system this leads to a lower voltage and lower performance. These conditions are called standard test conditions. You see it if power is related to standard test conditions, that you have put an index P. That means under these conditions this power could be reached, and this, for example, is 1 megawatt peak. So the first exercise was which distance between two rows of PV modules has to be kept in order to avoid shadowing, at least during midday for the whole year. So in summer we won't have any problems because the sun is rather high, but I think the worst case is 21st of December in the northern hemisphere. But while we are going to Brazil, southern hemisphere, it's not the 21st of December. It's also not winter there, it's summer there. The worst conditions is then at 21st of June. There's the lowest position. We have a position which is 23.5 degrees south, and also the elevation angle to the module is also of the module is also 23.5 degrees. So first question we already almost answered. Does the module has to be directed towards north or south? So we are very much used to see it from the northern hemisphere. So all the modules look towards south because there is the sun. But in this case, while the location of the installation is on the southern hemisphere, we have to face north. So that's a bit different, and so the azimuth angle is not 180 degrees, it is 0 degrees then. So the requirements for midday of the day with the lowest sun positions of the year. So as I just explained, it's the 21st of June. The direct irradiance should not cause any shading on the first rows of the module. So this means this alpha, as you saw on this graph before, this should be exactly as high as the sun on midday, on the lowest position of the sun. Then we have some data of the module. So the data, the modules have 300 watt each under standard test conditions. They have a length of 2 meters and a width of 1 meter. And then there's another question, which requires less space, the horizontal or the vertical mounting, and how much area we need to make a PV power plant with 1 megawatt under standard test conditions, or 1 megawatt nominal. And then there's another question, if we do not use the 23.5 degrees of elevation angles, but 10 degrees only, whether we save some area and how much is the saving of the area. So let's start. So, so just a copy, the gray part. This is here. We approach it like this. So we calculate the suns at the critical elevation angle. This is worst case. That means we have the lowest elevation angle of the sun, which is then equivalent to the lowest or the smallest alpha angle. And this means that it is the largest distance between two rows. And for the southern hemisphere, this is the 21st of June. The sun is then at midday 23.5 degrees north of the equator. This is our summer, because it's approaching us. Maximum it gets towards north is 23.5 degrees. Then the angular difference between the zenithal position in Rio, it's minus 23.5 degrees. Because Rio is located at 23.5 degrees, and additional 23.5 degrees, that's the sun position away from the equator, because it's north of the equator. So additional angular distance of 23.5 degrees. And we have then 90 degrees, minus 23.5 degrees, minus 23.5 degrees, and that's 43 degrees. So our alpha is 43 degrees. So you see this alpha here in brown color. So this is our angle. So we put in the numbers here. So we have the distance, d1 plus d2 is L. This is our length of the module or width of the module. This we have also decided later whether we mount it vertically or horizontally. Then the elevation angle of the module or the receiver, which is 23.5 degrees. And then the height and the tangents of this angle alpha of 43 degrees. We can simplify that. Then we have only L, and because we substitute H, and then we have just cosine of gamma E, and plus sinus of gamma E divided by tangents of alpha. And just if you put in the number, so this is 1 meter, we say is the length. We've mounted now horizontally. Cosine 23.5 degrees plus a sinoid of 23.5 degrees divided by tangents of 43 degrees. And that's then 1.345 meters. That's our distance we have to the big D. We have to keep between the modules. So D1 is 0.917 degrees. It's just if you go rectangular. Can we use here the mouse here? Okay, we can use it here. Just if you go down here, this is D1. This is most of the distance, 0.917, and then the part from the shadow is quite shorter, and altogether we have here 1.345 meters. So this was already answered. So it says the module has to be directed towards north or south. Just a repetition, during the year the sun bounces between 23.5 degrees north and 23.5 degrees south of the equator. So north is sure in our summer. This is 21st of June, and at 23.5 degrees south of the equator, it's on 21st of December. So for position of the sun, of the equator, the solar module sees most of the sun when they are inclined towards north. Second part of the questions, so horizontal or vertical mounting. So if we just calculated now, first we calculated horizontally, then this length at the cross section has been 1 meter. If we now mount it vertically, our length at the cross section is 2 meters, and altogether we have a distance we have to keep at 2.69 meters. So the distance requirement between two rows is now double, but it accommodates the double amount of modules, or double the power, and at the end this relative space requirements remain the same. The numbers of modules for 1 megawatt, so we have the total power 1 megawatt, and we have 300 watt each one, so in total we need 3,333 modules. Then we have the area requirement, so we have a width of 1 meter, and the distance 269 meters including distance, and then we need 8,965.77 square meters. So what would be the relative saving in a required area if the module elevation angle would be 10 degrees only? So we just put in the number 10 degrees, gamma E is now 10 degrees, and if we put that in, we have distance we have to keep if the module is now at 2 meters, and then it's 2.342 meters. So you just see that there's 1 meters and 2 meters written, and yes, so the distance is a bit shorter because it was 2.69 meters, and so we have a factor of 0.87. That means, in other words, that we saved about 13% in space to do the flatter installation and the lower shadowing losses. That's the end. Thank you very much. We hear us next week for the second lecture, the second exercise. Probably I put it all together in one video, exercise plus lecture. If you have any ideas for improvement, just don't hesitate to send me an email via the poll system or write something on the YouTube video comments. Thank you very much. Bye bye.